All right, here we go. Word problems for 6-254 we'll start with. And we're going to use the drawing that they did in problem 53. We want to find the distance A between the planes. So we're looking for A. When angle A is 11 degrees, B is 20 miles, and C is also 20 miles. So this is a straight law of cosines problem. A squared is equal to 20 squared plus 20 squared minus 2. 20 times 20 times the cosine of 11. And so we'll plug that straight in. 20 squared is 400 times 2. There's 2 of them. That's 800. Minus 20 times 20 is 40 again. 400 minus 800 cosine 11. So let's see what we got. 800 minus 800 cosine 11. And you should end up with 14.69. But that's for your A squared. So go ahead and square root it, both sides. And you end up with A is 3.83 for our final answer. All right. Engine design. An engine has a 7-inch connecting rod. So we're using this diagram down here. So this rod here is 7 inches. Use the law of cosines to write an equation giving the relationship between x and theta. So x is going to be this length, and theta is our inside angle. So let's go ahead and use our law of cosines. We want to find the angle opposite the 7 inches. So 7 inches is going to be by itself. 7 squared is equal to the other sides, one of which is 1.5. The other one is x minus 2, 1.5. X times the cosine of, what's our angle? Theta. And so we'll end up with 49 equals 1.5 squared is 2.25 plus x squared minus 3x cosine theta. And our job in this problem is to clean this up. And so if we have an x squared problem, we can move this around and get 0 on one side. And so let's minus the 49 from both sides, and we'll end up with 0 equals x squared minus 3x cosine theta minus 46.75. So that's our answer for A. All right, using that, right, x is a function of theta. That means we want to get x all by itself. If we have a quadratic, remember we can always do the quadratic formula to solve for x if we're equal to 0. So let's go ahead and do that. X is equal to the square root. Sorry, getting ahead of myself. Don't forget about our negative b plus or minus. So what's our b? Our b here is 3 cosine theta. So negative 3 cosine theta plus or minus the square root of b squared, 9 cosine squared, theta minus 4. A is 1. C is 46.75. All over 2A. So we've got a pretty ugly setup to start, but we can move this around and clean it up. So we're going to have, actually, I'm looking in the back of the book at their answer. They're okay leaving it just like that. Okay, so we can be done with B. Alright, for C, go ahead and put this in the graphing calculator. So let me pause this for a second, and I'm going to bring up the graphing calculator. Alright, here we go. So let me plug in for y, and our equation here was, let me go up and turn off our plot. We're not doing a scatter plot. Our equation is 3 cosine theta plus or minus. Okay, so in this case, let's start with the plus. The square root of 9 cosine theta squared plus, and if we go back in here and clean up this 4 times 46.75, it ends up being 187. So that's a little easier to put in here. So we've got that. And then let me close our other parentheses, and we divide the whole thing by 2. 2 times 1 right here. All right, so go ahead and graph it, see what we get. Nothing showing up right away, probably because I didn't do a very good window. Let me jump back in here. So our x value, we'll start at 0, and our x max, we're doing cosine here, so we at least want to do 1 period. So let's at least do 2 pi. So 2 pi. And it changes it for you. And then our y minimum, let's start at 0. And let's think about what our amplitude could be in this problem. So we're multiplying. And, God, it's really deep in there, isn't it? So let's start with 100 just to see. And we can zoom in from there. Alright, so clearly 100 is too tall, and so we can do a zoom fit. Went too far. And zoom fit adjusts for your y values for the top and the bottom, so you get a nice curvature just like this. And so then part D says use the graph in part C to determine the maximum distance the piston moves in 1 cycle. Okay, so the lowest it is right here. If we do the trace on that, it looks like our lowest point is 5.5. And let's go up and find the highest point on here. And 8.5 looks like the most it's going to be. So it says in this problem to find the maximum. And so the maximum is the highest point on our graph, so 8.5 would be our max. Okay, so a lot going on in this problem, but really it just starts from this law of cosines based on this initial internal triangle. All right, let's keep going here and move on to 58. Let's look at our awning design. A retractable awning above a patio. Door lowers at an angle of 50 degrees. So they show us our 50 degrees here. From the exterior wall at a height of 10 feet above the ground. So we've got our 10 feet here. And no direct sunlight is to enter the door when the angle of elevation of the sun is greater than 70 degrees. So when we have 70 degrees here, we need to figure out the length of the awning, x, necessary to create this situation. Okay? All right, so we have a triangle, and it's really this triangle here that we are looking for, and so we need to use everything we have. Got this distance also coming across. Everything we need to know about law of cosines to figure this out. So we do have a number of angles going on in here, so we can start, if we're looking at our triangle, I'll redraw it down here. This is a right angle, and we do have right, so we have this right triangle, which is here, but it also extends out onto this triangle here, which is really what we're going to want to work with. And we know that this angle here is 50 degrees. If we can find any of the other angles and sides, we're going to be in business, because ultimately we need to find this side x. Alright, if we know this is 70, then by the law of parallel lines, we also know that up here is 70 degrees. And we can subtract from 180, and we end up with this is 60 degrees. If we could find any of the side lengths, we'd be in business. And because we know this big triangle here, and this inside angle is 20, let's draw that tall triangle. 10's our height. 20, if we can find this side over here, we'll be in business. From 20, we have the opposite over adjacent, so tan 20 equals y over 10. The tangent of 20 is 0.36. So y, the side here, turns into be 3.63. And so we can use law of sines actually to finish this up to find x. We can say that 3.63 over the sine of 60 equals x over the sine of 70. Plug that in, move it around, you're going to end up with 3.95 for x. A few different ways to solve that problem, but that's the way I chose to do it. Alright, 60. Alright, so we want the area of this parking lot. We don't have a formula for the area of a parallelogram, but we do have the formula for the area of a triangle. So if I cut that parallelogram in half, if I can figure out this third side, we'll be able to use Heron's formula to figure out half of the parallelogram, and then we can double it to get the total area. And so we should know how to find x. That's law of cosines. X squared equals 70 squared plus 100 squared minus 2 times 70 times 100 times the cosine of 70. Let's plug it in. 70 squared plus 100 squared minus 2 times 70 times 100 times the cosine of 70 is 10,111. .72. Take the square root, and you get x is 100.56. Alright, so we got three sides of a triangle. We can use Heron's formula to find the area. First we're going to find the semi-perimeter. S equals, add up all your sides. And divide by 2. I get 135.28. And then we'll go Heron's formula, which is the square root of S, 135.28. S minus A, so 135.28 minus 70, 65.28, times 135.28 minus 100, 35.28, and finally 135.28 minus 100.56, 34.72. Multiply them all together. Take the square root, and I get 3,288.92. But remember, that's just one of the triangles. We also have to get this triangle over here. So we're just going to double it, times it by 2, and we get 6,577.85 for our total triangle. Parallelogram. Alright, last problem to go over on the even, 62. You want to buy a triangular lot. And it measures 1350 by 1860 by $24.90. The price of the land is $2,200 an acre. How much does the land cost? Remember, an acre is, well, not remember, I don't know why you would know this, but they're telling us an acre is 43,560 square feet. So let's find the area first of all. Semi-perimeter first. I'm going to add these up and divide by 2. I get 2850. Let's do Heron's formula for the area. S minus A, S minus B, S minus C. You can plug in the numbers. And I get 5.981, so that's roughly 1.2 million acres. I'm sorry, not acres, square feet. And so let's go ahead and divide that into acres. So divided by 43,560. I've got 28.3367 acres, and at 2,200 square feet, I'm sorry, per acre, times $2,200, we're going to end up with a sale price of $62,340.71, and that will do it. Try the odd problems. Questions, we will talk about them in class.